everyone. Welcome to the latest in CODA's webinar series. My name's Shaun Sadler. I'm the General Manager here at Centre of Decommissioning Australia, or CODA, and I'm delighted to introduce this session, which addresses one of the pivotal challenges facing the decommissioning industry, not just here in Australia, but worldwide. It's generally recognised that the safe, effective and sustainable abandonment of wells typically accounts for up to 50% of the total cost of decommissioning programmes. So anything that we can do to help us improve the efficiency of this process without compromising our relentless focus on safety is of great interest to the industry as a whole. One of the things that's really captured the imagination of the industry is the use of alternative barrier materials as part of the well abandonment process, in particular the use of bismuth alloys. And today's guest presenter is from an organisation that's become particularly synonymous with this technology, our partner BiSN. So I'm delighted to welcome BiSN's VP of Technology and Operations, Dearmon, who's going to help us explore the transformative potential of BiSN's bismuth-based wel-lok technology in the decommissioning landscape. Everyone in the audience, don't forget to load up your questions for Jake in the Teams Q&A or chat box. And without further ado, Jake, many thanks for joining us today, and over to you.
My name's Dearmon, VP of Ops Technology here at BiSN. Been with BiSN for about 8 years now. So started with the company when we were doing some of the original field trials, which, operators in Australia were part of some of those original adapters of technology here. So I've seen it from that into the company we are today. So I'll go ahead and give you guys an overview of the technology as a whole. So we're going to start pretty simple there, and then I'll dive deeper into some of the technical aspects, and we'll go through some case studies, particularly around the P&A sector, but also a couple of intervention options as well. So we will go ahead and get it started. So in my mind, the BiSN technology really rests on two main pillars. And the first pillar is bismuth-based alloys. So those are the actual alloys we are melting downhole to achieve seals. The other pillar of technology for us is the thermite. So a thermite heater is a chemical reaction heater. It's very exothermic, so it releases energy and heat to be able to melt those bismuth-based alloys. Now, those two pillars can be combined in, limitless potential, and can serve different applications throughout the life of the well cycle. But it's really those two pillars of using a thermite heater to melt a bismuth-based alloy that all of this revolves around. So why bismuth alloys? Well, bismuth-based alloys have a few advantages at BiSN that we use them for. So the first one is it has a low viscosity, very similar to water. So what we'll see in this video is we're actually pouring that molten alloy into a funnel. Eric here in the alloy department is pouring it on top of a metal table there. And when he flips it over, you can actually see all of the imperfections of that table still on the alloy. So that's a function of that low viscosity. It's similar in a downhole sealing environment where we either want that alloy to penetrate through a small perforation tunnel or a microannuli, or even a wellbore tubular that might have some imperfections in it. That low viscosity of the bismuth alloy allows us to do that. Couple that low viscosity with a high density, and it's a really good pair. Bismuth alloys are very dense. They have a specific gravity anywhere from 9.5 to 10.5. So they're very, very heavy. This high specific gravity actually allows the bismuth alloys, coupled with that low viscosity, to displace wellbore fluids. So any solids or anything that might be around that plug when it's a liquid actually float to the top. And in this next video, we'll see Eric again in alloy floating a steel bolt. No, that's not aluminum. That's a steel bolt that's floating in that pot of molten alloy. We've used that bolt for probably a couple of years now. And you can actually see these demonstrations live in one of our manufacturing facilities. But that steel bolt really just shows you, conceptually, it's hard to grasp what a 10SG fluid is. But that's where our bismuth alloys are. In addition to the low viscosity and the high density, bismuth alloys have probably the most valuable property in that they expand when they go through the phase change. So bismuth is one of the rare metals that actually expands volumetrically between a liquid and a solid. And we're all familiar with that property in water. So when we leave a Coke can in the freezer, overnight and it explodes, that's because the water is expanding roughly 9 times volumetrically between a liquid and a solid. Now, pure bismuth is around 3%, and alloys of bismuth are even less. But that volumetric expansion through that phase change is what we're relying on to actually form that seal. So in this video, we'll see we're actually pouring liquid alloy into a bottle here. It's a glass bottle. And after it's full and we fast forward a little bit, we see that cracking. And that cracking is actually the volumetric expansion of that alloy. It's inducing hoop stress around that bottle. And it's actually that force of expansion that's cracking that glass bottle. Now, obviously, downhole, we're not trying to crack casing, but, there's a lot of metallurgical differences between the glass and casing, but that's showing some of that volumetric expansion in that glass bottle. If we look at the other pillar, and that's thermite, nothing's new about bismuth alloys. Some of the first patents we found going back 40 or 50 years were actually filed by the Schlumberger brothers, where they were looking at using bismuth-based alloys to seal different applications downhole using electric heaters. Electric heaters, you have to have an umbilical back to surface, or you're running E-line with high voltage. It's hard to get a lot of energy into that heater to be able to melt it. There comes the thermite, which is a chemical reaction of iron oxide and aluminum that once it's reacting generates a lot of heat, and it has an enormous heat density and energy density that it has in it. So we're able to use that thermite to actually very quickly melt these alloys. Now, traditionally thermite's been around for over 100 years, and it wasn't very sophisticated for a long time. They used it downhole, they used it on railways to actually weld materials together, as well as military applications where the only thing they wanted to get out of the thermite was to make sure it burned. Obviously, we have to control it a little bit more. So in the next video on the left-hand side, we'll see what happens if you just take normal thermite and put it inside of a heater and ignite it, and it does bad things to the heater. But here at BiSN, we spent the last decade doing a lot of research into thermite, and we actually make all of our thermites now in-house. We're able to sort and go through our quality control process, really refine the particle size distribution of the thermite, put different additives into it to control how it's burning, how much energy it releases. So we were able to tame that really high energy density source into a useful application for us. So on the left-hand side here, we're seeing the thermite burn. It's burning through the heater. Obviously, we don't want that downhole. That's not good. On the right-hand side there is one of our thermite mixes we use every day in that same heater pipe. And you can see how it's controlled all the way down. We're able to focus the hot spot of that heater where we want it, and able to actually melt the alloys in a way that's beneficial for us. So that's kind of the two pillars of technology. You combine those two together and you get what we call the wel-lok technology. So in this video, we have the same controlled thermite and heater with some alloy cast in it. You can see as that thermite burns from the top down, it's melting the alloy. That molten alloy falls off the heater. Eventually, it all melts to the bottom, where in this particular case, like we do in a lot of our plug and abandonment operations, We actually remove the heater, that thermite heater, from the center of that alloy plug. That's to keep one material or one barrier material, rock to rock or casing to casing, and we don't have that heater left on the inside. Flash forward, you see that same expansion property in this Pyrex tube. That's the alloy solidifying and actually creating that hoop stress into the system that gives us that differential seal that we're looking for. I guess the last thing I'll bring up before we go into some of the specifics and some of the case studies, when it comes to our technology, is the difference between bismuth alloys and how they bond downhole. So there's two main ways you can do this. There's metallurgical bonding versus mechanical bonding. There are other companies that look at metallurgical bonding. Metallurgical bonding is where you actually create a bond between the barrier metal and the steel casing in this situation with intermetallic compounds. It requires a very clean surface. Usually the introduction of fluxes must be free of oil. So you think about soldering, how that's kind of done in a lab. Not that it can't be done downhole, but that's not what we do at BiSN. We prefer to use a mechanical bond that we see here on the right-hand side. That is really just a force of expansion, so a normal force, coupled with a coefficient of friction, almost like a swage or something in there. And that is what's actually creating that differential seal. Doesn't require the most perfect condition when it comes to casing. So, whether or not you have imperfections on the casing wall, the fluids that you're setting downhole. So, all of our alloys and downhole applications that we use right now, we prefer to use the mechanical bond approach to it. So we'll cover that. On this slide, we just have an overview of deployments. So, there's come a long way in the last 800 years, or 800, the last 8 years. We're rapidly approaching on 500 commercial deployments here. I would say the majority of our deployments every year still focus on plug and abandonment. So represents about 70% of the business we do. With that said, though, we still do quite a bit of intervention and completion work in the earlier life cycle or the earlier stages of the life cycle of the well. And then the new carbon capture and storage situation that's going on. Actually, I've recently completed the first 2 commercial deployments for those applications. So a good mixture across the board and in different geographies. If we look and boil down to Australian deployments in particular, they represent about 25% of our commercial deployments. They were a local development there, and they were some of the early adopters. So I want to say we were on commercial runs number 15 or so when we actually started getting involved in the Australian market. Right now, it's been mostly plug and abandonment and intervention activity so far. But we've done work for super majors and some of the local operators here, onshore and offshore. So very good mixture coming out of Australia for the last 5 or 6 years. Because of that continued success in Australia, we have recently, thankfully, opened up our Perth manufacturing facility and customer experience center. So here you can see a picture on the left-hand side. It's a full manufacturing facility, as well as the customer experience center and an operations depot. So all of those videos you guys saw earlier, you can see that in person. Just get a hold of Andy there or one of our business development team guys, and they can set up an appointment. But the key here is, before last year, deploying in Australia was difficult. We were looking at 3 to 4 month logistic travel times with equipment that was manufactured out of Houston or Manchester. Now we're able to source all of that locally, and the response time on getting tools out of the door has gone from 3 months down to a week if we have everything in stock there. So the addition of that facility in Perth has really helped us respond quickly to to recent inquiries out of Australia there. When it comes to tools, they go all over the place. So on the bottom right there is what I would consider one of our traditional kind of bread and butter P&A tools. So this alloy cast on heater example here is what we would use to seal inside 9 5/8 or 13 3/8. So that's kind of our typical tool size. We run a lot of those in Australia as well. In the middle, you see Big Bertha. That's the largest bismuth plug ever made and ever run out of the Gulf of Mexico here. And there'll be a case study on that I'll talk in a little bit more detail about. But that was a 20,000 kilo tool there to seal a 36-inch conductor. And then there's actually a third tool in this picture up at the very top, which was designed to seal inside 2-inch coil tubing. So we have a full buffet here of sealing tools all the way from 1.5-inch diameter all the way up to 36-inch. So just kind of shows the scope of what BiSN can do as far as sealing in different sizes and different geometries. Going on to the next, we're not just about P&A. On the left-hand side, I'm not going to go through every one of these applications. You can go on the website and watch some of those videos, but all of these applications here are different tools to accomplish different objectives, whether it's in the original completion stage all the way to P&A. I think it's important, and one of the highlights I love to bring about that slide is a lot of these applications were actually co-developed with engineers and operators that were early developers of BiSN. So we'll talk about a packer repair tool later on, in the presentation, but that's an example of us working with a client and a client coming to us, having done previous work, understanding those two pillars of technology of bismuth alloys and thermite heaters, and coming to us with a new problem. And hey, can we try to develop, and commercialize the tool to solve this problem? So, a lot of these applications have actually been bred out of, collaboration with other service companies and other operators, looking at different ways and novel tool designs that we can use, thermite and bismuth alloys to solve wellbore problems. On the right-hand side here, we see the biggest new buzzword we hear around BiSN, and that's the CCS game. So, that's something in the last six to 12 months that's really gained a lot of traction with operators and regulators around the world, where it's just another use of well stock that we can come into and transform that well through some different applications, different plugging technologies to be able to use that as a CCS situation. So that's another thing we're starting to get pretty big into. I like to say outside of the lower 48 here in the United States, every other market knows how big P&A is. Australia is definitely one of those. You guys have seen it time and time again. Some of the original, work that kick-started BiSN in 2018, when we really started to gain traction, was from the P&A market, and it was from clients that have gone in and spent tens or hundreds of millions of dollars, doing P&A the traditional way, and coming back 3 or 4 years later, seeing, the first time didn't work. And we're starting to see that, within the last couple of years, across the industry, not just with BiSN technology, but operators and regulators really taking a, initiative to look at P&A. How can we do it right the first time, versus doing it cheap and having to come back again? So, the slide was really just to highlight, the P&A market as a whole and how big it's getting across the board. CCS is, a little bit newer. So that's what we're getting a lot of inquiries from now. I know there's a lot of projects in Australia. I couldn't speak to every one of these, so I have Andy here. But CCS across internationally is becoming a big deal. And we're starting to get more and more commercial deployments on our side. And I'm sure that's going to be a big theme within the industry in the next 5 to 10 years, is using some of these extra well stocks in CCS applications. So we'll start diving a little bit more into the technical here. So pretty much the rest of the presentation will be case studies, some from Australia, some from other regions, but we'll start off with this one. This was kind of what launched BiSN in 2018. So this was a 34 well campaign, about 55 total plugs, ranging from 2018 into 2020 off Western Australia. There were a couple of different configurations that it was focused on, but the majority of completion sizes were 9 5/8 by 13 3/8. You can see where we set about 46 plugs in that, as well as a couple of other different sizes that we had to come up with. So for this particular case study, this is the first big volume work we had. Some of the challenges we had, going into the project is obviously, the challenge here was annular, sustained casing pressure from shallow charged gas migrations that when previous cement plugs have been set in, had channeling problems and still had that sustained casing pressure. A challenge for the BiSN technology was obviously a remote island location. So it was relatively remote up in Western Australia. We were having to mobilize equipment from Houston and Manchester, so that's quite a bit of logistics challenges trying to get the equipment there 3-4 months ahead of time. At the time, BiSN was conveying all of our plugs with wireline, and these tools were over 2,000 kilos each, so pretty heavy tool to run on E-line back in the day. Now, luckily, we have pretty much every conveyance option at our disposal, but at the time it was E-line. We had solid one material barrier required. So I mentioned that a little bit earlier when we were watching the video on removing the heater. Prior to this campaign, all of our tools were leaving that thermite heater as part of the plug. But because of regulator requirements, having a single material, rock to rock or casing to casing in this situation, we needed to find out how to remove that heater, which required us doing some testing and development work here in Houston to actually design a reliable solution and a reliable tool that we could melt all the bismuth alloy, but still remove that heater out of that molten plug to leave a single barrier across it. I guess the final challenge, which last year we improvised on or improved on, was no regional facility. So trying to suffer through 3 months equipment transit times and stuff like that required a lot of planning up front. I go through some of the storyboard here. So obviously, we start with a well that has sustained casing pressure and compromised cement going up the backside. Our typical operation would be going in and section milling anywhere from a 5 to 8 meter window. So a little bit better than a 30 meter that you would for cement, but we would section mill that 5 to 8, 9 meter window. We'd go in and underream that clean. We would then set a base for the base of the bismuth plug. Sometimes that would be a cast iron bridge plug inside the rat hole down here. Sometimes that would be an annular or an inflatable up inside the section mill window. We did a good mixture of both. You then go in with an E-line tool down the depth. We would activate that heater and then remove that heater from the molten plug anywhere from 15 to 20 minutes after activation. So pretty quick burn cycle there. And then remove that heater out. Some of the summaries from that. So like I said, 34 wells, 55 plugs. See here, these are not small tools whatsoever. Mostly done through section mill windows, heater removed, pretty much replacing 30 meter cement plugs by 1.5 meter bismuth plugs. And after an 18-month watch and verification of all those, all the wells are deemed a success. So that was a really good thing for BiSN. We've done a lot of work like this since. I know this final well of this campaign was in 2020. We do about 40 of these a year, give or take, around the world. But I really wanted to show this because this was the beginning of BiSN. This 50 plug deployment is really what kick-started the company 5 or 6 years ago. Really commercialized the product. So very, very thankful that campaign went well, and everything everything went well for the operator as well. The next case study we'll talk about is the packer repair tool. So I mentioned earlier, this is where an operator we worked with before came to us out of Western Australia and said, hey, look, we have an idea. We've got a problem downhole with a production packer that's leaking. Do you guys think you can help? So BiSN, we had developed some alloys into a bead form, so we don't have to make it in cast alloy. We actually made those alloy beads before for different applications. So we looked at this, from the very beginning with the client on, is it possible? What can we do? That started out with, obviously a financial assessment of, do we want to bring in a workover unit, to do it, or what are the cost savings with, BiSN trying to do this rigorously? Obviously erred on the side of BiSN, but this was a R&D type development project. So, to do this actually required some testing. Nowadays, quite a few of our clients come in and we have something that's immediately off the shelf that we've run before, and we can go straight to a production work order, or we have those tools in the shop ready to go. But even now, we still have clients that are coming to us, or service companies, and we're wanting to push the boundaries on existing technology. And here in Houston, we have the ability to test pretty quickly in any wellbore conditions, different sizes, 1.5 all the way to 36, pressures up to 25,000 PSI, temperatures from 0 C to 180 C. So, for this particular PRT development project, we went through a full testing campaign, which culminated in a final SIT with a third-party V0 test here, and that's what we see at the bottom, or the actual envelopes here, with 3,000 PSI of gas pressure, 200,000 pounds of compression tensile loading during that testing. So after this SIT, we actually got ready to go to the field. Here's where we can kind of see the storyboard of this. So you have a leaking packer. You deploy the beads into the annulus. Those beads settle on top of that packer. We then run in with a thermite heater on the inside. We activate that heater, which warms up this entire area, allowing the alloy beads to melt without damaging the completion, because you are warming through that production casing or that tubing. And create a new packer in situ without having to pull the completion. We can see the logs here from that particular deployment. Over here, we can see the acoustic logs after the BiSN setting. So good confirmation here on acoustics and gamma ray response that we got a full 360-degree coverage all the way around before we actually pressure tested the plug and move the equipment off location. So some of the learnings there is there's, tremendous financial benefits to the client, over $30 million saved there compared to a hydraulic workover unit, plus the time waiting for that. Post-deployment log clearly, saw that on acoustic and gamma ray that we had good plug. The SITs were, completed with V0 testing after several iterative testing with different heater designs and stuff we had done at BiSN. Saved about 7 months on getting that well back online compared to waiting on a hydraulic workover unit. And really proved for us, that was one of the first commercial deployments where we actually successfully verified the integrity of BiSN because it was in the annulus, and we were able to run some of the logs to actually see that alloy behind the production casing. The next case study we'll look at is what we call a cement repair tool. So very similar concept almost to the packer repair that we just discussed, where we want annular isolation. But in this case, we don't have a production casing that's free to drop alloy beads, right, from surface. In this case, we actually have, cement running all the way back up, back to surface. This is a very common tool we run here in lower 48 and in Canada, where we have consistently bad cement jobs with sustained casing pressure at surface. Traditionally, the methods to remediate that would either be a bleed and lube method from surface or a squeeze cement job. So what we're doing with the BiSN alloy is essentially similar to a squeeze cement job, where we're going in and perforating or gaining access and somehow to the annulus at depth. We then go in with a BiSN tool and melt the alloy through those perforations into the backside, flowing through those microannuli and channels. The benefit of using BiSN over traditional squeeze job would be the low viscosity of the alloy. We don't have to rely on high injectivity rates like you would with a resin or cement to actually get the material into those fissures, through those tiny perf channels, into those cracks in the cement. The low viscosity of the alloy itself, coupled with the high density, allows it to do that. So in this particular case, it was 7-inch completion by 8.5 or 9-inch open hole. We needed annular zonal isolation, so we wanted to create that annular isolation of gas percolating up through compromised cement. To begin that, we look at a CBL to determine the ideal target zone. So what is the likely formation it's coming from? What kind of cement do we want to set in? Depending on the application, sometimes we want to set in a well-cemented situation. Sometimes we want to set on top of cement if there's a top, like in free pipe, but use CBL to analyze a lot of those wells. Once again, perforations to gain access. We've used perforations, we've used jetting tools, we've used some other technology out there in the market. The main thing here is giving us access, and as much access as we can behind that production casing to get to that compromised cement to set that BiSN alloy. One of the unique things about this campaign is it was a mixture of wells that some actually needed the option for re-entry, whether that's we want zonal isolation and we want to go recomplete the well or reperf a well at a deeper depth, or such as a CCS example where we need to seal everything above that zone, but we need access below afterwards. So what we're able to do in this situation is go in and actually perforate. We set a base for the perforations, whether that's cast iron bridge plug or cement top. Most of these wells, we actually use top of cement. That was already inside the production casing there. We go in and set a bismuth plug on E-line, which allows that alloy to actually flow into those perforations. We remove the heater, and then from that standpoint, from a P&A perspective, we could leave the plug like this, which we did on some wells, or in other wells where we needed access all the way back down, we go in with a special BiSN mill that's alloy friendly, and we actually mill this back out to the full bore, so you're not handicapped by a restriction like you would get with a patch or something afterwards. So it was a mixture of wells on this particular campaign. Some that we milled through, some that we didn't. The next case study, I'll have to be a little bit selfish and bring it back to the Gulf of Mexico here. But this was, once again, another example of one of our operators who had been with us for a long time that came to us with a very unique challenge, in that they had a conductor dry pipe that was in the shallow water shelf, so about 300 feet of water, that they had inherited. That conductor dry pipe had been cut about 15 feet above the mud line, and there were some P&A plugs deeper in there, but the top of the 20-inch P&A cap was about 60 feet below the top of the conductor. So we had 60 feet of room to work with that was open to the Gulf of Mexico. So contamination was a risk, all kinds of barnacles and wildlife inside there. And they wanted us to be able to go in there and set an environmental plug in that well. Preferred that it would be rigless. So it was a big challenge. They gave us about 2.5 months to come up with a solution, get it tested, and actually deploy this in the field. So I will share a quick video on that.
When I founded BiSN, it was to take on the biggest challenges in the oil and gas industry. This project was one of the biggest challenges we'd ever faced at BiSN.
Project Atlas is about building the biggest bismuth plug ever run.
So this tool was designed to seal a 36-inch conductor just 250 feet down to the mud line with no well control.
Well, the well, it's already cemented in place and it's still bubbling. In that space, the best thing you can do is set a bismuth plug.
It's something that no one's even thought of or attempted before, and the challenge here is really weight.
About 20,000 kilograms total, with 10,000 kilograms of bismuth alloy on it and about 2,000 kilograms of thermite.
So my previous job, 1 gram of thermite was a lot for us to work with. Now here we get to work with 2,000 kilos, which is super exciting.
Everything starts in the machine shop.
We want to make sure that the plug we form is a perfect plug for your well.
There was a lot of pride at the end of the day when we stood around that tool, because everybody had a hand in it.
There are 4 critical phases to this deployment. The first phase was overboarding. Phase 2 of the deployment was a subsea handover. Phase 3, it's time for activation. After a short 55-minute burn cycle, it was time for the final phase of the operation. After the tool was safely returned to surface, an ROV was utilized to monitor the top of the conductor pipe to ensure that the tool had functioned as intended.
A successful deployment, 0 bubbles, and our plug will last forever.
It culminated in a smooth, safe, and successful deployment, which protects the environment and makes for a happy client.
These forward-thinking operators are looking at sealing the wells not just today, but forever.
So that explains it a little bit better than I could. But here again, this is the schematic of that. So we had, a couple of feet to work with above the mud line. There were some 20-inch P&A caps on top of the existing 20-inch in there. And really the only way to address this problem, cement couldn't do it just because there was not the length, unless you brought a rig in to be able to circulate clean fluid over. The only real option was a BiSN plug up here in the very top, which is what we were able to do. Give you guys a quick overview. So this is some of our typical size tool comparisons. This was some of the Aker BP tools we ran to seal 20-inch casing. This is a direct cross comparison of this giant 20,000 kilo tool that we were able to deploy in the Gulf of Mexico here. Here's a picture of a really good looking guy right here, watching the tool successfully come back on board after all of the alloy was melted off. Here's just to put it in scale, all of these 5-gallon buckets were full of thermite powder that actually went inside that heater. I believe the actual energy calculation was enough to power 20 homes for 13 days or something. So it was an enormous amount of energy released in those 55 minutes to actually melt 10,000 kilos of bismuth alloy. The final case study we'll look at right here is just a straddle. So it's a unique concept that we developed for an open hole straddle for a CO2 well. So what we had here was a 5.5-inch casing that was cemented all the way down to depth. There was, in Canada, there was a CO2 injection well. This well had previously been abandoned. There was a CO2 flood enhanced oil recovery well located about a quarter of a mile away, that over time, that CO2 flood had actually come in and compromised the 5.5-inch casing that used to be part of this wellbore envelope. And they had pressure at surface inside and in the annulus of that 5.5. So they wanted to try to remediate that problem with BiSN. So what we were able to do is actually started with going into the well and removing the existing cement plug and doing a log. And during that log, we actually found that 20 meters of 5.5 was not only corroded, it was completely removed. And that was the 20-meter formation interval that CO2 was traveling in. So the only way to protect the wellbore both below and above was to set a bismuth plug below that charge formation interval and then another one above it. So what we're able to do here, we can see here where this lithology zone that the CO2 was flooding in from had completely corroded this casing. We're able to run a log and see where that zone was. Design some tools to actually be able to seal down in the open hole below that interval of CO2 injection. We set the plug, removed the heater. We then needed to give us a sacrificial spacer because we did not want to put 20 meters of bismuth in the well. So we put cement over that CO2 zone and set another bismuth alloy in the formation directly above that. So you ended up with a straddle that protected the lower wellbore from the upper wellbore. So one of the challenges here was that we needed to actually customize and have tools available on site that once this logging was done, we could change the amount of the alloy because we didn't know the open hole sizes that we could deploy on the fly in a remote location. So we were able to send up a variety of heaters with the alloy in a pelletized form so that based on the log results, we could adjust the amount of alloy we intended on melting in a particular zone based on the actual open hole log dimensions in that zone. So we had to have some versatility in the tool functionality that we sent. I'll end up the last couple minutes because I know this is focused towards a P&A group. So there will be some questions over regulators, what we've done in the past. So BiSN's worked with a lot of the regulators around the world, OJ UK, NORSOC, PSA, BESI here in the United States, as well as in Australia, on partnering with operators to provide all of the documentation needed to the regulators, all of the testing we've done, the previous examples. So that's something we do every day. It's not uncommon. Some of the documentation and stuff that we have to provide from our side, we have a qualification document. So this is qualification of bismuth alloy plugs for plug and abandonment. And this was originally made for OG UK, as well as NORSOC and the PSA to actually get barrier classification on the Valhalla DP abandonment campaign. And this is some of the barrier requirement performance that we were able to achieve on that campaign for Aker BP in the North Sea. So here was a 30-well campaign that we completed in 2021. It started years before that with a lot of the plug and abandonment requirements, some of the testing, alloy qualification testing, actual tool qualification testing, a 2-year field trial. But we can see here on the left-hand side, these wells had previously been abandoned, all 30 of them. And by 2020, we had almost every single one of them having problems. And those problems being pressure at surface from shallow gas formations entering the wellbore. The abandonment campaign that we did over 2020 and 2021 rectified all of those problems enough that they could actually cut the conductors above the mud line, remove the top side of the structure, and they continue to monitor those wells every year with ROVs and continue to have good success and have shown no bubbles in all 30 of the wells. So just a good resounding case study, and one of the key things that we go to regulators with is some of the actual track records of BiSN alloys being used for barriers in different environments. So without that, I guess we'll hand it back over to you guys for any questions.
Thanks very much indeed, Jake. It's a fantastic overview and really good to see a little more in-depth material around the case studies. Thanks to all online. You have been submitting your questions, so there are a few things here for you, Jake. And so the first one is to do with the focus on mechanical bond. When there is no full confinement downhole, how does one establish the mechanical bond?
When there's no full confinement.
I guess if you're in a situation where you're struggling to sort of maintain, if it's an unconfined situation that you're trying to remedy, and I think some of your case studies talk to this a little bit in terms of the use of interim packers or cements to establish that confinement. But what is your how do you establish that mechanical bond on that basis?
So I'll address it in two different ways, okay? Because I guess I could interpret the question in two ways. The first way I could interpret it is how do you get that mechanical bond in open hole, right? If you don't have casing, if you're just an open hole, right? And that's a good question, because if we're trying to seal an open hole, it really depends on the lithology, right? So we target a very low perm, very low vertical permeability cap rock environment. So if you set a BiSN plug against a unconsolidated sandstone or something, you're only going to be as good as the vertical permeability on the outside of that plug. That would be the first way I could interpret it. And, if it comes to open hole setting, it's important. Similar principle, you're still inducing stress. So you're compressing up against that formation, almost if you can envision compressing again, like a packer does, or compressing a filter cake or something like that. It depends on the lithology on that, how much stress that formation can take. If I interpret it on how do we confine that alloy and keep it from running down hole, for example, that's where, that specific gravity of 10 is very heavy, right? So it's going to want to go south. Fortunately for us, once it gets below the bottom of the heater, right, it starts cooling off very, very quickly. So the heat from a thermite heater radiates radially, very good. The heat transfer down, not so much. So a lot of times, the alloy itself, once it comes in contact with wellbore fluids, especially below the bottom of the heater, it starts to solidify. Nonetheless, we still, in a lot of our applications, still use some type of base. Sometimes I mentioned that might be a cast iron bridge plug. Sometimes that will be an inflatable. If we're using inflatables, we do a lot of work with IPI. They're an Australian company. We do a lot of work with them internationally. We will actually use their inflatable at the bottom of a section mill window. We will space above around their fishneck with alloy beads or steel beads just to give us a buffer from their elastomer, right? And then we will actually use that that flat base of BiSN beads to actually set the seal on top of. Hopefully that answered it.
I think you've covered a variety of different situations there. We've got another fairly specific question, which I'm hoping you'll be able to talk to a little bit. Are there any concerns with galvanic corrosion when the bismuth is in contact with casing for an extended period? Are there any controls or considerations we'd have to make to prevent this? So galvanic corrosion.
Yes. So as part of the alloy qualification program that I was talking to, that's a public document. We give it out to a lot of different operators. That tested 2 or 3 of our common alloys, and a big portion, so half of that was creep testing, so prolonged creep testing. The other half was actually corrosion testing. So during that corrosion testing, galvanic corrosion was one of the test samples for all of the alloys in there at different rates. And yes, galvanic corrosion does happen. But the rate of which, that galvanic corrosion coupon samples that we have data from is so low It's not even concerning to the barrier over a 3,000 year period, which is what a lot of the OG UK or NORSOC requirements stipulate. The same thing goes for acid corrosion testing as well. So that's all data we have. We can send that out. We've sent a lot of different alloy samples that we use for P&A out to these third-party testing companies. But yes, galvanic corrosion, it happens, but it's such a low rate in the alloys that we tested that it's not a concern.
Okay, thanks for that. You've probably spoken to this a little bit. Has there been any records or applications where BiSN plug is placed against the formation, open hole, instead of against casing? It might be worth just reflecting on how many times you do that compared to how many times you put it against casing.
It's starting to become more popular. So originally we didn't do a whole lot of open hole plugs. There's just a lot of stuff we can't control, just due to the nature of operations, right? It's becoming a lot more frequent now. I would say we average maybe 20 to 30% of our P&A plugs are set in open hole. Considerations for that. Certainly the lithology. So where are we setting it in, right? We have to make sure that we're setting it in a caprock type environment. We don't want to set in an unconsolidated sand. We want to set in something that's pretty competent. The other consideration is the prep work that goes into setting one of those open hole plugs. So, we don't want to be fighting against a filter cake, for example. So in a lot of those situations, what we're doing is we're going in and section milling, and then we're going in with wide sweeping underreamers. I say we, another third-party service company, going in with underreamers to actually underream out a few inches into virgin rock. And the way we treat that rock before we set the bismuth plug, right? So, once we want to do that, we want to flush that window, make sure that, we don't have the hole falling in, and then go down and set that bismuth barrier across that open hole section. So, typically with those open hole considerations, we do try to set longer plugs. So we have a little bit more safety factor. If we know we need a 2-meter window or a 2-meter plug, say, to hold a certain pressure differential that the client's looking for, we don't have to add a huge safety factor for unknowns if we're inside casing, right? So we can underream, the casing ID is probably going to be exactly what it should be. When we're in open hole, we have to add more safety factors. So that means making a little bit longer plug because, if we go in and underream and we have a little bit more washout than we intend, that could mean we're setting a slightly smaller plug than we want to do. So that's one thing is it's prep work on the well, how we do it, the choice of lithology, and then from our side, making sure that we have some safety factor and we make sure that we're creating a long enough plug, even if we do have some extra washout, that's capable of holding that differential we're trying to get.
Thanks for that. It's great explanation. Now, as you guessed right, there's a couple of questions that have come through in relation to how the regulators view the bismuth alloy plugs. One of the questions around, has the regulator accepted 1.5 meter plugs, or are operators pumping cement on top of that still? And then just generally the regulator's views of bismuth versus cement as the choice of sealing materials. And I think, you spoke to some sort of global work that you have done with different regulators, but interested to know in particular, I guess, what's been your experience here in Australia?
Yeah, so, regulators in general, we're seeing across the board international that we're going from a very black and white, a very set standard. So, a decade ago, all the requirements were pretty set in stone. We need a 30-meter cement. We need a 50-meter cement plug. We need, and it was very, spelled out. And now you're seeing a lot of the legislation change over, to a more risk-based approach. And that's honestly good by the regulators because they're almost pushing the ball back into the operators' courts, but it's allowing them to use alternative barriers. So on a case-by-case basis. So that's where, a lot of times we have to work directly with the operator and the regulator to get approval for, whatever the specific case may be. And it is a mixture between regulators. So, we have regulators that will approve BiSN as a barrier in the North Sea with nothing else on top of it. We have regulators that will approve that in the Gulf of Mexico, and clients will do just that. We have regulators that will approve it in the Gulf of Mexico, but intercompany operator standards require them to actually put, so internal operator standards will require them to put a 30-meter cement plug on top or 50-meter, whatever it may be. Australia is one of those cases where, we're still getting quite a bit of, we're getting classified. So I know recently in Australia, and I might have to cede to Andy on this because I'm more based over here, but we are setting dual barriers, so independent BiSN plugs on top of each other to classify as, a redundancy barrier. Certain sizes, that's 1.5 meters. So if we went to bigger casings, that would be more than 1.5 meters. I believe on some of specific to Australia, I may be mistaken, but I think they're still putting some cement on top. So we're going in the right direction. That's kind of what within Australia, that's what we saw here in the Gulf of Mexico and in the North Sea, where at the beginning of it was, okay, we will allow you to use bismuth and you can shorten the cement plug. And then after enough of those, we actually got some of the regulators to start going into, okay, we will accept just a BiSN as the barrier. You can forego the cement.
Thanks very much. We've just had one final question come through. If you can talk to this, it's a fairly lengthy question, but I'm going to read it out for you, and let's see if we can work through this in the last couple of minutes. An internal BiSN plug is one element in a P&A barrier envelope. Can you give examples where BiSN has been used as a primary reservoir P&A barrier? And if so, what length of plug was set? And how was the integrity of the cement on the outside of the casing assured? What was the minimum length of cement that was accepted by the regulator? And which regulator accepted this? So that's about 6 questions in one. But certainly talking to that particularly primary reservoir P&A barrier and the verification piece that goes alongside that.
Yeah. So as of right now, we have not done a primary reservoir barrier. Those are usually deeper in the well. A lot of our P&A is up shallow. So a lot of our plugs are set in bigger casings and section mill. When you look at primary well barriers down deeper that are set, usually at the beginning of the P&A process on coil and stuff, we just have not got a lot of operator interest thus far. There's other ways to do that. So right now, the majority of our interest is in some of the upper barriers where we're spending a lot of, or the client's spending a lot of rig time actually section milling those bigger casings, whether that's single string or dual string. So as far as classified by a regulator as a primary reservoir barrier at the bottom of the well, no. To address hopefully soon, and we are working with some clients on that, but thus far, no. One of the key elements there was a good point to bring up, and that's a regulator question we get asked quite frequently, is the impact on the cement on the outside of the case. Say we're setting inside casing and you have cement on the backside that you're considering part of your envelope for the barrier, right? That is a very common question we get from regulators. What we typically do is work with the operator themselves and their cement subject matter experts. And what we're able to do with our modeling is show them the temperature and time duration that cement is going to be exposed to that temperature over that 1.5 meter length. Now, remember, you're typically talking hundreds of meters of cement there, but we can give them that data for here's what you would expect in that cement, temperature-wise, over the plug setting process, whether that be an hour or 6 hours. And a lot of times that's where, operators and us have to work in conjunction to try to get the regulator to buy in and accept that. But it is a common thing we get quite a bit. But I think that's just, across the industry, whether it's BiSN or other companies, those are the types of challenges, all of us are getting when it comes to getting regulatory approval and trying to get a lot of these technologies across the line.
Listen, thanks very much indeed for that answer and for the last hour, Jake. It's been absolutely fascinating. And thank you all in the audience for coming up, staying with us and coming up with some really interesting and challenging questions. So it remains only for me to say thanks once again to Jake Dearmon and all of BiSN for bringing the information around this technology. And thank you, and we'll see you next time for the next CODA webinar.